Did you finish the test, John?
Joe, you're late.
I
What?
know. Did you finish the test?
Which test? Yeah.
So everybody's done the test?
I have no idea. But everyone thinks there isn't Zoom. I told them there is Zoom, so they'll slowly join.
Okay. It will not. I don't think it'll be a super long one if not everybody has finished the test.
Okay.
I should have this book here. Oh.
Why do you sound like something like bad happened?
Something really bad happened.
Why?
I didn't have lunch.
Bruh. Oof.
So I'm hangry. All right. Is this everybody that we're getting? Can you?
There's gonna be more.
Yep. Could I ask you guys to get page 5, chapter 34, if everybody's done their test?
We don't know if everyone did it though.
Well, did anybody not?
Well, Mr. Hendrick, you can check.
Oh, that's actually very true. I am in completely the wrong headspace at the moment. Okay, open up. No, I don't
Bruh.
Are you okay?
Does he look okay, guys?
I mean, I'm not.
No, I'm in quarantine.
I feel like you've been tortured by Benji and CJ.
That sounds very true.
I feel like, yeah. I feel like you haven't slept in years.
That sounds very.
13 people who've handed in.
And then what?
We're missing 2 then, right?
And then what?
3. No, 2. I don't know. 3?
Okay, let me see. Who hasn't handed in?
What are we talking about?
So I have the people who have handed in are Rebecca.
That test.
Yeah, I need to upgrade your answer, Rebecca. Rebecca,
Yeah.
Jonathan, G.A., Kim, Ji Young, Billy, Brutal Bros. Oh, Dylan. Lucy, Yedam, Hanbi, Jesse, Kyle, Yoram, Hajin. So I'm missing. How many people are in the class? What's the thing? Who am I missing?
Why aren't people joining?
There are a few more, because I have to let them in.
Great.
All right. Karina.
Yeah.
Can you ask everybody else for their answers on the test? I mean, can you go do the test?
Oh.
Mr. Hendrick.
Ask for answers, bruh.
That's probably not the right thing to say. That's probably the wrong thing to say. Bad misgender. Okay. If 13 people have done it, and I have how many people in the class?
15?
I feel like there's people missing all the time.
So is it, if we're done, do we like stay in the call?
Yes, please, because the only reason I want to find out who's done it is so that I can figure out whether or not I need to start chapter 34 yet.
I hope no one does it then.
All right, well, I've got 13 people here. There's 3 people that have it,
So we're not gonna continue?
Hyorim's done it. I just need to know who hasn't. Hyorim's done it. Hajin has, Lucy has, Dylan has, Yedam has, G.A. has, Ji Young has, Tim. Do I have a Tim? I don't think I have a Tim. So Tim, that Lee boy has, Hanbi has, Jesse has, Kyle has, Elsa. So Tim, Elsa, and Karina. That works for me. Tim, Elsa, and Karina. All right. Yeah. Okay. So I can start with you guys then. All right. Okay. This is the start of the class. Tim, Elsa, and Karina, you need to hand in the test as soon as possible. Let's move on to chapter 34. Okay. So to start with, can someone tell me what voltage is again?
Electrical potential.
Okay. What are we trying to describe there?
Electrical potential energy per
Energy over
charge.
charges. Yes.
Well, you're talking to me in what's the word? In definition terminology. If I was to have a brick and I hold it up here and I talk about its potential energy, what would you say, what would it be the equivalent voltagey sort of thing?
What's the question?
So if voltage, so let's go with this. If I want to talk about if I was to say the voltage in terms of physical mass, it would have to do with your potential energy per unit mass. Okay? Whereas volts is equals to your electrical potential energy per unit charge. Okay? Now this all sounds very well and good, but basically if I give you a physical picture of this, it's how far away this object is, how far it's being moved through the gravitational field. But there's another way to look at voltage instead of having it as your position in a field. Let's have a look at the concept of water. Let's say I have, and this is exactly what you will see on page 532, which I'll stick up here so you got it. Okay. So page 532 has this example where they're looking at water. No, don't give me text, give me the draw thing. Thank you. No, give me the draw tool, you silly device. I swear I'm going to turn you into a calculator. Does anybody else yell at their devices or threaten them?
No.
No? Okay. It's just me. Okay. So if I was to have a container, I'm actually just going to use the line. If I have a container filled with water, there we go. If I have a container filled with water, can you see the potential difference in this system? Can you see the potential difference here?
Isn't that like, isn't the water should be the same level? Why is it?
Oh,
different?
yes. Which way is it going to flow?
The right side.
Yes.
Okay,
I mean, like, it's common sense. Right?
Someone give me it. Yes, of course it's common sense. Science is common sense based on attached to observation. Give me an arrow. Which direction is it going to go?
Wait, let me draw. Yes, very nice arrow.
Oh, very interesting.
Okay, so you can see voltage not just as your position in the field, but it can almost be a pressure. It can almost be a pressure that moves your current. In this case here, the current of water is being made. You're talking about it being similar to a current the reason why they use the word current for both water and for electricity is because of this sort of example. Now, if I was to add in another part to this system, let's say I add in a pipe which goes through here and it connects to an impeller pump. So if I connect this to a pump that pushes the water back up through here, pushes the water up through here, you're going to have depending on how much energy you have in this pump, you're going to have water traveling through this system, right?
Yeah.
This is a similar way to the way a battery works. So a battery or a power source moves the current through the system, and it just keeps moving. Okay? That's the way a current works. And the thing that powers that is this voltage difference. So if you consider this as the number of electrons, these number of electrons want to move over to this region here. You don't have to keep pushing water in to get this to move. By simple virtue that this has a higher voltage than here. Let me get the spotlight button because you can't see it. Simply because you have a higher voltage here, the current is going to flow this way. Now, this could be an application in a light. It could be an application in a motor. It could be an application in a set of speakers. It could be an application, anything that requires electrical power. It might be running a computer. Simply having a higher voltage in the input, and the power just went out. Did the power just go out? Can you guys still hear me?
Loud and clear, sir.
Okay, so my internet's still on. I just had something weird happen to my screen.
Mr. Hendra, I think some people are waiting to join.
Get in?
Yeah.
No, I've got everybody in.
Oh,
There's nobody in.
Wrong code.
Nobody in the.
said she can't get in.
There's nobody in the waiting room. Just can you resend the class code through the chat, please?
It's in the announcement thing. I put it up.
Okay, so it should still work. So that's the basic idea of an electric current. The things that move are known as electrons. Positive charge doesn't move. So everything that's going through here is your negative charge. That little lines, yep. So the things that are moving are these little negatively charged particles. Okay? It's not a positive charge that moves. I'm not very good at drawing this bit. I'll just leave that. Okay. When you have current in motion as opposed to current in a static situation, when you have current in motion as opposed to current in a static situation, you don't tend to have a buildup of static electricity. So you don't have a buildup of charge on your conductors. Your conductors will most often have a zero voltage. Let me repeat that again. If I take a cable, an electrical cable that's carrying charge through it, this has almost zero voltage. I do not feel any static electricity, even though this is currently powering an object that requires electricity. So the charge that's going through here it doesn't stay there. You're not building up charge inside a conductor. This has almost zero static electricity on it because the amount of electrons going in is equal to the amount of electrons leaving the system. So if I have 1 million electrons go in and 1 million electrons leave, what is the net charge?
Zero.
Zero. Quite often you get a zero net charge. Okay. All right. Finally, we get into where do you get what functions as the pump? Let's go back to let's just ask this question to everybody for a second. What do you remember about ions?
Not much.
All right. Can I break you into three groups
Yes,
of
you
four? And
Is chapter 34 harder than chapter 33?
it's different. So I'm just going to assign you into 3 rooms. I'd like you to come back to me with an idea. How does your understanding of ions in a solution, how would that give you an idea of how electricity might flow in a battery? Okay, I'm going to just break you into rooms. I'll come back in 2 minutes. You can tell me, how does your understanding of ionic bonds, how would that help you understand the way electricity could flow in an ionic solution? Okay.
Bro.
Oh my gosh, that was scary.
Yep. So,
We just got the question and we just unmuted our mics.
okay. Well, I'll leave you to it. I'll move to the next group.
Just can you send it again
Yeah, can you send the question?
in the chat this time?
Good, I didn't. Yeah.
Metallic. Hi, Mr. Joe.
Okay.
Um,
B. Why is that not controlling B? All right. I don't know why it's not.
you are very laggy. Were we supposed to know this, or are we supposed to find it in the book?
Yeah, no, this is stuff that you should have known from last quarter.
Oh.
Wow.
Is it because the electrons are moving through and it's
Oh,
transferring?
that one.
Is it that
Okay,
one?
I think you guys got the idea. I'm moving to another breakout room.
Bro.
How are we going? Hello? Hello? Why is everybody
We
silent?
can't hear very well, and it's raining and all the sorts of places, so we're just doing it over.
Okay, just a hint. Think back to last quarter when we were talking about ionic solutions, metallic solutions, and covalent bonds.
We're using the chats.
Okay.
Hello, Mr. Hindro.
Hello,
What's the
Mr.
question?
Hendro.
Okay. So,
I scratched myself.
what are your ideas?
What was the question?
What's the difference in the way electrical charge flows within an ionic solution as compared to a metallic conductor? Go back to last quarter.
Isn't ionic thingy the way they like move? They don't share, but they like
Do you
move
remember
from
the
one to another.
Do you remember the three types of bonds we talked about in chemistry? You had
Yes, ionic,
Ionic,
covalent.
covalent, and metallic.
how would electrons move differently in an ionic solution compared to a metallic conductor?
Uh,
Okay.
Maybe ion.
You can do this, Dave. You can do this. Okay.
Mr. Joe,
Yo.
does when you're saying ionic, do you mean basically any non-metallic?
No, I'm not talking about
Okay,
sugars.
Dylan, you're wrong.
You've got covalent bonds as well, which are like plastics. They don't conduct
Oh,
anything.
that one. Oh, I remember now. I can remember now. Yes.
Hey,
Ah.
John, you can explain it now.
Not really, because ionic is different from just non-metal.
So wait, which one's the ionic part? Because
The I don't know. There was covalent and ionic, right?
yeah,
Or
Yep.
am I? Yeah.
covalent, ionic, non-metal, and metallic. Ionic is the
No. Non-metal is divided into ionic and sorry.
also. I was
Wait.
correct.
So wait.
Yes,
then what do you
John!
mean, Mr. Andrew? You
Oh,
said
hell yeah.
no.
Non-metallic bonds. Non-metallic bonds are covalent and ionic. And ionic bonds are peculiarly, normally between a metal and a non-metal.
I see.
So sodium is a metal. Chloride is a non-metal. Sodium chloride is an ionic bond. Sodium chloride is salt. Now, if you had absolutely pure, 100% pure distilled water, if you had 100% pure distilled water, it would not conduct electricity.
Nice.
Why does it conduct electricity then?
Because of the ions and everything mixed inside the water.
Yeah, you've got,
That's conductive.
yep, you've got,
Sugar.
yes, but it conducts, no, sugar is not conductive. It
Oh,
conducts
salt.
the salt conducts differently than a metal would. Yeah, try to think how.
Different. The electrons are placed differently, so one's more conductive and one's more not.
More not.
I'm sorry, I meant not, but more came up in my mouth, so I just had to go with the flow.
Can someone else help Dylan?
Is that wrong? I'm pretty sure it's wrong
Can
based
someone
on
else
your
try and help
expression.
Dylan?
Jonathan knows.
I've helped him enough times.
Can I have somebody from group 2 help me? Group 2 that had Billy, Tim, etc.
I didn't hear the question.
You sorry?
I didn't hear the question.
Can you tell me the difference between the way electrical charge moves in an ionic solution as compared to a metallic conductor?
Oh. Okay.
Why do
So,
you think I stuck you in the breakout rooms?
yes. Wait. I have the answer. It's metallic solutions. Metallic solutions.
No. An ionic solution and a metallic conductor. Electricity can flow through both of these.
Yeah, one just kind of goes through the water, and then one goes through the metal, and so it's okay, right? So like if the electrons in the metal is like loose, and so it pushes it one end, and it goes out the other end of the wire, and then it's how it goes to the metallic thing, goes down to the solution. It's got the ions in it, and then it goes in one part of the water, and then it goes out the other side of the water. Something like that.
Okay. I'm one of these people that expects that if you've learned something once, it sticks in your head. So
No,
maybe
that
I'm.
does not happen.
Iya. Aduh, corona. Okay.
Whoa.
If I have a,
I virtually got corona.
if I've got an electrical conductor here, and I've got my little electrons going through my electrical conductor. Now, does this when the electrons go through, are they tied to any of the atoms?
No.
No, they can move freely.
Yeah.
What happens if I was to have why? Oh, why does it do that? Okay. If I have a little what's it called? A beaker solution, and I have it filled up with salt water. If I have it filled up with salt water,
Yes,
the
rocky salt water.
yep. So you have some sodium ions, and you have some chloride ions as well. If I then connect this to a circuit, if I then connect this whole system to a circuit, I don't want that color. I don't want it. Let's have it purple. If I then connect this to a circuit,
Mm-hmm.
there's a battery, etc. If I connect this to a circuit, what's going to happen to the ions?
Is it gonna flow?
You're gonna get charged.
What's going to
Yeah,
happen?
it's probably gonna shift and transfer and keeps on flowing.
The ions will move. The chloride ions will move towards the positive electrode. And the negative ions,
How do you get a negative ion?
chlorine is a negatively charged ion.
Always?
Yes. What's its valency?
Ah.
So if you have something that is free to move, like if electrons are free to move through a conductor, they're not tied to the atoms. Here they are. The ions will physically have to move themselves. You actually physically have to move the salt across the electric field. Which one's faster?
Metal for sure.
Charge moves faster in a metal conductor because the electrons are free. Free to move. Okay? And over here, In an ionic solution, the electrons and protons are tied to their atoms, ions. I'll just say ions, to their ions. So they will move at the speed their ions move. Okay? Okay? So this is I needed to remind you about the way ionic solutions work, because the way you have most batteries work is that they are ionic. Most batteries that you find will have some sort of ionic properties to them. What type of battery do you have in your phone?
Lithium battery.
Yes,
Lithium.
lithium. Sometimes it says lithium-ion battery. Okay, so that lithium-ion will have to physically move. The way you charge up a battery is you get these ions like this. If I took this system out and I disconnected this, and I took out the battery, if I took out the battery from this system, why doesn't maybe control, no, I need to actually select both. Okay. If I took the battery out of the system, there's nothing holding those ions there. They would slowly float back. But if I was to attach something where electrons could actually flow, let's say I was to add a light bulb in the middle here. If I was to add a light globe here, what would happen is that your electrical current would flow back because there's a potential difference. Remember, this here would be, let's see, that was positively charged, which gets the negative ions going there, and the positive ions went there. So this is currently negatively charged here, or equally charged. As these leave, that means that the electrons are going to move that way, back through to here. Okay, so you'll have electrons go back that way. This is basically the principle of the way a battery works. Okay?
Is there no in between?
Sorry?
Is there no in between?
What do you mean?
There's like nothing in between. So like all the negative and all the positive just separate each other.
You remember the water level thing? Which here, these water levels are different. This end, that end there being negatively charged, and this end here being
Positive.
this end here being positively charged. Okay?
Okay.
So if you have a difference in charge, you're going to have the electrons move. And that's where you get the flow. Yes. And the power here is where the ions then move. This is why you have a DC battery that can give out certain amounts of electricity at a slow.
Is ions the protons and neutrons?
Ions are the entire atom, or the entire.
What about the electrons?
Sorry?
Oh, wait, that's the electrons. Never mind.
In an ionic solution, the electrons and protons are tied to the ions. They will move at the speed of their ions. Wait, why is that not correctly? See, their ions move. That's why. They'll move at the speed their ions move. This is why you don't have an instant boom of all the electrons moving at the speed of light going through. You can have a certain amount of charge stored in a battery. Okay. So what's the voltage that you have at the moment in the country that you're in? What does Korea have?
How do you check?
It's either going to be around 110 or 220.
$550.
Where are you?
It says
Tajikistan.
220 when I look it up.
It should be 550.
I'm just
This
kidding.
girl. It says
you have- if you-
220 when I look it up.
It should say on your power packs and stuff. Are you able to plug your Indonesian electrical sockets into?
Yeah.
They match? You don't use an adapter?
Yeah. No. It's the 2 circle thing.
Okay, so it's exactly the same. That's nice. Your output should then probably be about 220, I think.
I don't know.
I'm pretty sure Indonesia is at 220 volts.
It is.
So America functions slightly differently in that they function on a 110 volt.
Why is it different though?
Why is it?
Dylan, it's like asking why do they use Fahrenheit instead of Celsius?
No. This one actually has a decent reason. So when you were first having when you first started having massive uses of electricity, America is one of the first places to implement it. New York City in particular, I think. They actually tried under Thomas Edison. He was trying to make a DC system in New York. It didn't quite work. It turns out that alternating current carries power much more efficiently over long distance, because AC current works differently from DC current, because instead of the current just going in one direction, it goes backwards and forwards at very high rates. Like it goes backwards and forwards 50 times a second. And your voltage is your average voltage difference from zero. So it spikes anywhere. If you got a 110 voltage thing, it spikes anywhere from 170 to negative 170 to negative 170, and it alternates, like it going backwards and forwards. DC current is where you push it directly through the system. We think it's probably easier to think of DC current because most of your devices turn the AC current into DC current. When I say devices, I mean things like computers, laptops, mobile phones. They turn it into DC current. But when you're transmitting power, like over on your electrical wires, a high voltage is much more efficient because you heat up the conductor a lot less. Okay. So we're up to section 34.4. We'll pick that up on Wednesday. I am trying to think of a activity that we can do here with a DC circuit that will not cause problems. All right. Well, I'll see you guys on Wednesday. I will be giving out the homework assignment. That'll be the last homework assignment for the year. And I'll try to get the test out as quickly as possible as well. So the sooner you get done, the sooner you're done.
Wait, Mr. Hendro, do you have finals?
There needs to be some sort of final for science here. I am sorely tempted to just have you guys tell me which would be the most applicable. The information in quarter 1, the lessons in quarter 2, quarter 3, or quarter 4.
Well, what's it gonna look like?
Do you? It's going to be an opinion piece. Do you think you'll use Newtonian physics, waves, the study of waves, and oscillations and all that, chemistry or electrics most in your chosen field?
And we need to write like an essay.
I'm trying to think of one that doesn't have as much essaying involved. You're over essayed at the moment.
Can we just write like one paragraph?
What if we forget the whole school idea and just have like a final party or something?
Let me think about it.
Okay.
Okay. All right. For the moment, thank you very much, ladies and gentlemen. I will get back to the grading.
Okay.
Grading of what now?
The essay.
History. Yeah.
Yeah. Okay, terima kasih.
Oh, also,
bos.
Mr. Andrews, so we're supposed to critique and fix our own essay in this week.
No, you critique somebody else's essay. Your fixing
When
of
do
your
we
essay,
fix?
the fixing of your essay is something that you do just slowly and slowly. The real time
Okay.
that I want you to fix it is that last week.
Okay.
Okay? Okay.
Wait, so John,
Yeah.
I send my essay to you.
Yeah.
Okay.
Okay. See you guys later.
See ya. Thank you.
Thank you.
Bye.
Thank you.